So the second presentation is from a representative from industry, our collaborator Ulf Hartmann, who has experience with suction technology and was working with UniGripper and provided us the tool that I mentioned. So he is working
for 10 minutes. All right, my name is Ulf Hartmann. I work for UniGripper, was the sales and marketing director for the past 5 years. And I still am for the next 10 days, then I'm off to my own enterprise, so it's going to be a bit more exciting. But yeah, the Amazon picking challenge for us was pretty much something to try out new industries and to get some more feedback from the academia. Yeah, UniGripper, for those of you who don't know, is a vacuum solution provider more than a gripper. We've been on the market for almost 20 years and have been handling anything from coils, steel coils, to packages, to cookies, to whatever there is on the market. And this order picking is pretty much new, I think, for the whole industry actually, but I'll get back to it later. What I was thinking of doing today is, basically to get a little bit more of an input of the reality. What's out there in the market, what is there, how it's done. So first of all, I want to define the different actors there are in the automation industry. Then we're going to go into the warehouse distribution centers, the challenges and the reality, which are existing nowadays. And then we're going to check the different type of grippers and what we've learned together with Rutgers from the Amazon Picking Challenge will be on the last bit of it. Who's who in the automation industry? First, obviously, you've got the end customer, which in the case of the Amazon Picking Challenge, you will see that this is quite really related to the Amazon Picking Challenge. It's nothing new on the market or in the world. You've got the end customer, which has a problem and presents this to the integrator, which in this case are the Amazon Picking Challenge teams. And those then pick the different suppliers, the robots, the sensors, the grippers, conveyor belts, which hopefully are not showing up in the Amazon Picking Challenge for a long time. And the normal way of doing this is then that the integrator chooses the components which to use, integrates the different components into one solution, and sells this whole package then to the end customer. This is how it works. This is the industry. This is also academia for the Amazon Picking Challenge, so there's nothing new there. Now we go back to the warehouse and distribution centers for order picking. How does it actually work? This is basically the usual layout that we see, or what we see in the industry for sending goods, basically for order picking. You've got, as I said, the order picking. Then you've got the emboxage of the packaging. It's the second step. And the third step is the palletizing. Now, if you look at it nowadays, you've got a declining number of solution providers the further back you go in the industry. That means that you've got a lot of solutions for that palletizing. You can choose whatever you want to. There are several suppliers on the market with different solutions. Then you go back, find a minor number for the emboxage or for the packaging, and then pretty new is the order picking. There's not a lot of solutions on the market for that right now, which is pretty much also why this whole Amazon Picking Challenge was created, I guess. Now, grippers. What kind of grippers do you have? You've got mechanical grippers, obviously. Usually the integrator designs these on his own. He doesn't buy them. He just buys the components, which results in there are many different solutions or different mechanical grippers as there are engineers working for these integrators. And obviously you've got also various different product sensing options. If you want to use torque force, the camera based, the visions based, ultrasonic, you choose it, you can integrate it quite easily into these solutions. You can see that there are different options. If you want to have a clamp system, a normal parallel gripper, there's a lot of solutions depending on what you want to choose. If we go over now to the vacuum-based grippers, you can clearly see we've got two options: suction cups, which is standard components. There's a high number of manufacturers, which results in pretty good pricing. And also as well, these are then to be integrated in a solution which each integrator designs himself. They rely usually on very high vacuum levels to create lifting force. We'll get to that later. And the product sample here, the most natural is then a vacuum switch, which then tells you how much vacuum was generated using foil feedback. And there is, however, in the real world, and I will get back to why I mentioned the real world, a risk of a breaking point between the products. Mainly because you always have the inertia trying to break away the product once it's grasped. You have to think about speed here, and speed is not an issue with Amazon, but in the real world it is. So this is usually a product issue here, that you have this breaking point when you move or accelerate with the robot at full speed, that the product tries to move away. Then you've got the so-called foam grippers, where we come in with UniGripper. These are usually project design, customized for each project. At least for our company, that's the issue, making it a lot more fast. The other difference between the suction cups and the foam grippers is that obviously you've got suction holes in the foam, which then create a very similar holding force or grasping force, but this force is then divided or distributed along the surface of the product. The foam also compensates for irregularities, so if you have some kind of irregular superficies, then you can still choose it. Foam grippers work best when they rely on a high flow rather than high vacuum levels. Just to give you an indication, usually the suction cups work in a normal environment with minus 700 millibars of vacuum. Foam grippers works best around 250, minus 250 or 300 millibars. Yeah. This also makes it much harder to use vacuum switches. If you have depends then basically again on the component of the vacuum switch, how accurate it is, because the difference between grasping and not grasping might be just minus 50 millibars, the difference between one and another. That's why it's much harder. But you don't have the breaking point between the product and the gripper, as it's completely attached, much more firmly to the product. So you can see basically suction cups, you just have to tell the manufacturer basically what kind of product you have, and they will tell you this is the suction cup for the product, and that's basically it. This means there are a lot of suction cups on the market. This is obviously now for a Swedish company, but our manufacturers are as many as suction cups basically. And here you can see already a little bit more advanced tool that we delivered. Just to give you an idea what this gripper did is, it works for, it is actually working here in the States, in Vermont for Kellogg's. This gripper, what it does is, the task is in the distribution center is these Pop-Tarts come in, we mix them basically. The robot goes in, picks them up, these are all lined up, the different grippers, separates them, puts them into a mixer or a layout, and then it is completely changed according to the order which is going out. As an extra, the integrator wanted that the tool then, because the conveyor belt, the secondary conveyor belt is tilted, so the tool itself is made so it tilts 5 degrees exactly. So it picks up, tilts 5 degrees, goes in and drops it off, and separates as well. That's basically the difference, and that's then also where we come in, finding solutions instead of just building components. Vacuum generation, you've got two different ones. Once again, I appreciate, from my point of view, it's very interesting to see that on the Amazon Packing Challenge there were so many vacuum cleaners. But obviously if you go into the real world or in this industrial world, there are other solutions. One is then the pneumatic generators, which are based on the Venturi system, called ejectors or Venturi style ejectors. Here you use compressed air, usually about 6 bar 87 psi is the normal standard. And you get a very high vacuum at around -7 millibars or 70 MPa. They have, however, a relatively low flow and a high energy consumption, because you have to think that you need electricity to feed the compressor, and that compressor then feeds the compressed air to create vacuum. So it's a bit more. Then we've got the electromechanical generators, usually called vacuum pumps, but in most of the cases, and when you see a vacuum gripper working, it's actually a side channel blower. Lower vacuum levels around -300 millibars or -30 MPa, and a very high flow. The advantage of this is that if you have them in a robot cell in the real world, it's a complete system on its own. You don't have to worry about the rest of the factory. And we've had many problems with vacuum or with the compressed air, where when they did the trials, the factory acceptance test, it worked fine, and all of a sudden they start up the engine or the factory, inside the factory, another bit of the factory which consumes a lot of compressed air, and all of a sudden instead of 6 bars we get 2. So the whole thing didn't work anymore. Amazon picking challenge then. We teamed up with Rutgers or Practice Lab. And the second one was then the combined tool, as I said. The biggest challenge for us here is that we get much more data which we can work with. That's not data transfer from you to us, but data from how it is presented to us, how the product is presented. Usually that's a fixed point, meaning that you don't have to go into a bin. You don't have to worry about the movement and how to retract it and place it. Usually, in the real world, you have it on a belt or in a box where you just go in, often with a Delta robot or normal smaller robot. Just pick it, put it on a conveyor belt, and send it on to the next stage, which is the ambulance order. That's then the biggest issue for us in this case. And as we see it, the biggest challenge for us is not the gripper, but the software. That's something that we don't see as much as a challenge. The gripper, just as the robot, will do whatever the software tells it to do. So that the biggest challenge is the software in this issue. Exactly as I said, there is usually a defined position and a clearly defined place where the plug is in order to pick it. Obviously, the more products you have and the more types of different packaging, the larger struggle to handle them all. And for the future, I am already envisioning a more capable tool, but again a combination of mechanical and vacuum, but lighter a bit more. But just to get it back now to reality, what the big difference is with Amazon Picking Challenge, and where I see the issue with Amazon Picking Challenge, is simply the presentation of the product. And with this presentation on how it is done and how the setup is done is basically for me a no-go as to automate. I would change the whole infrastructure of Amazon basically. Just to give you an idea, when you said that the best team had 1 item every 2 minutes. In Italy we're working now at the factory acceptance test, and I'm picking 7 items a minute. That's the picking rate we have, so that's a long way from where we're going to go, and it's also very long from the capabilities of the setup. It's simply the setup of the team or of the composition or the simple layout is simply not done for automation. Again, I think that for the future we will go into more lighter material as well, not only aluminum or steel, but go into more composites issues in the clamping, and we will have a bit more issues there. So, I'm a bit afraid to shorten time, but I think I compensated for you talking too long. Are there any questions related to the grippers or?
So I suppose for Amazon, it has a lot of warehouses already. It would be a big investment if it had to add additional infrastructure so as to automate the process. I think one of the motivations is to...
Yeah, I mean, the good thing with Amazon is that not all the warehouses are on the same level yet, so that's a good thing for them, I guess. Yes, definitely, there's still potential there.
So any addition what you would be changing to automate this process much faster from your side?
Well, yes, I would, one issue that you can do, for instance, is, or why we're so successful in Italy is that everything loose is presented in bags, and if it comes in a box, it's in a box. So it makes only up for 2 different types of products. So even if you've got like the little mesh pen holder, even that is presented in a little bag, which makes it possible for us to vacuum and to grip it. It's quite easy. Or even just put a label on it, a uniform label which has one defined size for which you can pick it. That would be a solution as well.
I noticed that for this for hand design, actually it requires a lot of this expertise, and for example, for each workpiece, you may design a different form of this gripper. But for example, in some cases, like the hand or the gripper used in a kitchen, and the gripper that you use in a mechanical workshop, definitely to require a very different form of functionality. Do you think that is, from your point of view, is possible to automate this process that from the task analysis to the form or functionality of the gripper?
Well, the advantage with the foam grippers is that the foam can adapt very well to different types of products. I mean, you have to think that we're handling in Sweden paper rolls, big paper rolls, both from the side as well from the top. From the sides, obviously it is curved, but we're still the same gripper, which is flat. The gripper itself is flat, but because of the foam, we're able to grip it from the side as well.
Yeah, but from my experience, for example, I have some like T-shaped workpiece. I need to grasp it, and then I order it from some like gripper manufacturing, and then they need to start to analyze this the size or the weight of this workpiece, and then they start to design and manufacture it. And from the time they started to receive my order and to the time that they actually send me the product, it usually takes like 2 weeks. But this is, for me, is still too long. I want to like make this faster. I want to obtain this gripper like within 3 days. Do you think this is possible for your company?
If you do it yourself, yes, but not with us. I mean, we have lead times usually which are 2 to 3 weeks, maybe 5 after the sign up of the design of the gripper.
That's actually for me is a bit annoying, because every time you need to wait for like 2 or 3 weeks, but this workpiece they may change like in the next 2 or 3 months. Like especially in this 3C industry.
What we had in Brazil was quite interesting, because we had a project where we had to design a gripper with picked small plastic details which go on shoes and stuff like that. Yeah. And those can change pretty much once a week, I think. Yeah. So what we did was make a base gripper. You can do a base gripper and then just change the last part of it, which then adapts to the design of the tool, which per se you can print out 3D by yourself, basically. So solutions are solutions to issues.
It's very similar solution that we work on. Okay, thanks.
So super heavier items, right? If you have the item in grabs, you turn on vacuum and use other means to hold it in place by moving. So that will save some energy, right?
Yes, what we do sometimes is that we have fork grippers, for instance, especially with oil, when you're handling oil, which is in boxes, we use a fork gripper and just have the vacuum on the side. Mainly just because the boxes might have some oil and then just open up. So there's definitely solutions that you can just combine. Energy-wise, I don't think, if you're talking about heavy industries in coil grippers, we're moving coils which weigh 7.5 tons upwards. And then just to have a small blower which is 9 kilowatts running is really an issue for the steel industry. You know? So yes, there are solutions for that too.
So, going back to the Italy solution, did you have insights like what really made it work faster? Like you were doing twice as faster.
Picking. Mainly the rubber is already quite slow. I mean, or slower. If you look at the speeds which you can achieve with the Delta robots versus the one with the the SDA-10, for instance, the Delta robots are simply made for speed, while the other one is more, that's the limit, which I really see, and I think Eric is nodding there. There are different robots for different tasks, and if you want speed, you have to go over to a Delta robot simply.
And your honest opinion about vacuum cleaners they used for?
Yes, I mean the vacuum cleaner is very cute, basically, and it does a job. But at the same time, you can just get a 1.5 or 1.4 kilowatt side channel blower, which is the same amount of energy use, but creates a lot more flow. So that's something that we're going to look into as well for next year.
So in your company, the gripper design require what kinds of expertise? Like we are in Team MIT and we have one mechanical designer and one electronic, but we spend a lot of time.
Well, what we do is basically, as I said, we present solutions. So you give us a task and we present a solution that we find is the most suitable one based on our know-how on the product. And now that we're going to have, or that I'm going to have more resources in regards to what other components I can choose for the gripper, we will be able to create a better gripper. Simple as that. I mean, there are even magnetic grippers out there which we can use if it requires.
So from a task assigned to the final gripper, tested gripper, you say it's about 3 weeks.
No, that's the production time for the gripper, but usually it takes, well, what we do in sales is already we basically envision the gripper, what it has to do, give that and off to our design department, which translates that into a 3D model somehow, or hopefully that they understand us, and that's then about a week that we take.
Thank you.
So our next speaker is Professor Jian Xiong. We Team MIT participated the Amazon BE Challenge with the Princeton Vision Group. Jian Xiong was a professor at that time, but now he has his own startup. Apparently he has some very good thing that can be commercialized. So let's welcome him.
Okay, thank you. Okay, today I'm going to talk about deep learning and 3D deep learning for robot perception. Since this conference is really about automation and robotics, let's talk about that a little bit. So how well can robot work actually today? If you ask journalists, this is how they think robot can work today. It's basically, you can imagine the Terminator is really here. But if I ask my engineer friend and all my scientist friend, they will also feel that probably not at the Terminator level, but maybe in a healthcare level that can give you a hug when you need one. When I ask my parents what robot can do today, they think that this is what robot can do today. They can make children and me very happy. But this is really difficult problem. What can robot really actually do today? Last year, DARPA decided to spend $100 million to get an answer. And this is the answer they get. Some of you may already watch this video, it's really funny. Hopefully you're not from Canada. And there's a lot of localization problem. You see, this is obviously a localization problem. If you just observe how meter is going to work. And this one, I think, is from the folks from MIT, where I also did my PhD. But the point I'm trying to make is a lot of mistake here, actually not robot mistake. A lot of mistake happening here is because of human mistake. Because if you look behind the scene, this is what's going on. For example, the MIT robot, they stream the video, the 3D point cloud to the server room, and people just control the robot. A lot of mistakes, not really any computer mistake. It's the human controlling the robot forget to turn off a notch on the knee of the robot, and they become going like this. But why do you need to have the human in the loop at all? It's because today's robots are mostly blind. the perception system is not really working very well. But hold on a second, if you heard about all the news, all the buzzword about deep learning, you know that there's a huge breakthrough in computer vision because of deep learning. With deep learning technology, we can, for example, image and object classification. Now you can get to a performance that is better than the actual human performance. So that's why there's a huge breakthrough in computer vision. In robot perception, we just say that it's actually not working, so it's less better to put a human in the loop. So I would say that robot perception is really difficult. Like for example, Professor John Lennon from MIT criticized that computer vision is really the computer CVPR, the flagship conference in computer vision is really computer vision procedure recall. People are overly obsessed to the numbers instead of really making something useful. Of course, some people even have more radical comments about computer vision. Okay, but going back into the more about Amazon Robotic Picking Challenge. Last year, all people here probably know that there's a report published there. But based on the pool in the report, all those teams after competition, they actually ranked perception to be the most difficult part of this APC competition. Yeah, I have to summarize that robotics really have a QR code problem. Right? For example, there's nice demo that Boston Dynamics actually made. They designed this Atlas robot that can do a lot of tasks, walking around, carrying heavy objects, losing it, and so on. But still maintaining very good balance. And in case it actually fall, it can still stand up and so on. So you can see that the robot control today is actually very, very mature. What is really lacking is really the robot perception. The robot perception part is still there's a lot of work to be done. Like here, the robot decided to quit this low-pay warehouse job and run away. But you can see to run away, you need to put so many QR codes on the door in order to let the robot run away. So what I'm trying to summarize is the robotic really have a QR code problem. My research is very simple, is to get rid of the QR code for robots. In particular, I want to bridge the gap between the computer vision community and the robotic perception community to build a really stable and working solution for robot perception, to make robot perception great again. Okay. So today I'm going to start by talking about the Amazon picking challenge, since everyone here really care about this problem. This year, as Peter just mentioned, we have partnered with Team MIT to work together. We use the ABB Robo Arm and then MIT team. They have very smart people design this gripper. And our job at Princeton side is mostly taking care about the perception system for object recognition and pose estimation. This is our team, and we have a nice picture with Peter standing here. So yeah, our lead student in our team is Andy Jen, who unfortunately is not here today. Our perception system is we use a RGBD sensor. It's an Intel F200 short range depth sensor installed on the gripper, and then we're going to use this. It's the only camera we use for everything. So system-wise, this is how we do it. First of all, we take multiple pictures. Even, for example, object in the shell, we take multiple pictures. We have the camera mounted on the robot arm, but we take multiple pictures of the shell. For example, let's say that this is the beam of the shell. You take multiple pictures. We take 15 pictures, and then we all use all the pictures for recognition. If it's in the storm, we also take some pictures. I think it's 18 here, right? 3 times 6, yeah. And then we use all the pictures together from multiple views to handle occlusion and so on to do better object recognition. Okay, after we take multiple pictures, for each picture, we try to have a segmentation of the target object for each object basically. We use a fully convolutional neural network for segmentation. For example, for this image, this is the layer segmented for background. Red one means high intensity for background. And this is, I think this is for the blue bottle, and this one is for this eraser. So we use the fully convolutional neural network for segmentation. Here is another example, like the duct tape. Our neural network output a segmentation mask for the duct tape. But this is only one source of information. This part is trained using neural network, doing that image segmentation in 2D. You input the color image, you output the mask for segmentation. But the other information we can use is actually background subtraction. That this is a special problem. It's not really a genetic object recognition problem because we know the background very well. We calibrate our robot so that our arm, when we take the fitting picture, is always have the same location with respect to the beam. In this way, we can subtract the existing image with the picture we took without the object there, and do background subtraction. You can subtract the object out. Of course, if there's multiple objects there, then you will definitely have multiple objects in the foreground. But then we can combine with this deep learning segmentation result to have a more robust solution. So, for example, here is the environment that with the book here, there's some object here. But if you do background subtraction, you can subtract that this is the background to remove it, and this is the foreground. And we combine this background subtraction result together. This is not a learning-based approach, basically comparing pixels, figure out whether the points are actually inside the 3D boundary of this beam, and then combine those results together with the deep learning result to get the final segmentation mask. Okay, so for each one, we can get a segmentation mask, and then combining deep learning the background subtraction, we combine together for multiple views, and then we also merge all the point cloud from all the views. Now, for example, for this particular object, we can identify this is the object in inches, and then this is the object. The next step is we need to figure out the pose. Right now, it's basically just a segmentation. You do segmentation on each image, you merge to have a 3D point cloud. And now we need to get the 3D pose in order to have the gripper to go to grab the object. So what we do is we use because this is an instance level recognition problem. We know the object, that's only that object ID is basically that. So we know the 3D shape very well. We can run ICP based pose estimation to fit the pose. So how do we get the 3D model? So in my office, I made this turntable in 5 minutes. I took a box and I draw a lot of random text, put a lot of sticker and a lot of pin there to create more texture. Then I put the object there, and then I take pictures while rotating this very simple turntable, and then I reconstruct it. I use a 6 key point to detect each point, and then for 2 images, I use the 6 key point to do matching, and then after that, I link a sparse bundle adjustment graph to run bundle adjustment to get the camera pose. After I get the camera pose, I fuse it using a KingNet fusion style algorithm to maintain a 3D spatial representation to scan the model. Of course, it always have a problem that the bottom part is not missing, so that's actually it's empty in the bottom part. Okay, but in this way we can reconstruct the 3D model and we get the 3D model using for ICP scanning. Now the next step is we are going to take this input point cloud. This is a pre-scanned 3D model, and we fit it using ICP. So here is some result. After the green one is the scan box, scan model, and then you fit it with the ICP. If using the ICP approach, that iteratively originally we try ICP, but the detail really matters. Like for example, the objective function is not standard ICP function. We engineer it in a way that, for example, including the occupied space, the free space, including whether the points are actually lying on the surface of the model. We have an objective function with multiple terms that we just manually choose which term to put what weight. My students spend a week tuning those weights to figure out how to better represent it, but it's actually working very well in terms of the pose. So, but remember we use a neural network, but how do we train the neural network? That's a problem. Like how do we collect training data? That's one of the biggest problems. Of course, you can take a lot of pictures. If you during training time we have the robot, I think Peter worked very hard to take a lot of pictures. But the problem is now how you label it. That's a more difficult, tedious task. Of course, you have the human manually click the segmentation boundary or manually label the 3D pose. Yeah, you can click the label. But we have so much data. If you label this way, it's very painful. So again, we apply we look deeper in this, look closer in this problem, and we apply the background subtraction to get the label. For example, if this is the environment, we subtract the background, either it's from the shelf or from the bin stove, and then we subtract the background, right? For example, given this need, we can apply our background subtraction, and then we get a segmentation mask for free just by taking a picture and taking a picture with the empty shell, and then you do background subtraction, you can get the mask. In this way, we don't need to manually segment the environment and gather a lot of training data. So during training time, each time we only put one object inside the bin, and then we know which object is, that part is known as a label. But for the segmentation mask, we just applied our background subtraction algorithm, and we get this segmentation mask and use it to train our system.
But if you have this automated process for doing the leveling, why do you need a neural network afterwards, since you are getting an answer?
Yeah, but this is just during training time. During training time, the human will tell you this is a blue bottle, right? After you get the label, then you can use it as training data to train the neural network.
So still a human here tells you what object?
Yeah, the human, when you put the blue bottle there, you will say that this picture belongs to blue bottle. So we have the human to label the category, but we add the background subtraction to generate the mask. In this way, we train a segmentation network that we can use it during testing time, just given the image to tell me each object what they are. So during training time, it's only one object each time, but during testing, you can run multiple objects, yes.
So you don't have training for that, right?
Say that again?
If you have multiple objects, right, well, you will be confused because you don't have training for that kind of.
When we train our neural network, it's only one neural network for all the objects. So although each picture only have one object, but there are many different pictures. Like this picture comes from that object, this picture comes from that object. So locally, because it's a segmentation network, if you look locally, each small patch is always belong to one object. So during although the training data do not have clutter, but you learn how to do like clutter seed. So you can, like, for example, that picture, like for example, this is a very cluttered environment, but after you train it, you test it, you can figure out which channel, like this is the ducktail channel, and then you can generate the mask for ducktail.
Wouldn't it be advantageous though to build a neural network, separate neural network for each object, because it would fit better to the data for you?
Not necessary. Then the neural network cannot take care. During training time, if you train one object with the background, then suddenly there's a new object comes in, it may fail actually. You don't.
It doesn't generalize it.
Yeah. So it's better to train the neural network that can take care of all the objects plus the background. And then they can identify different objects. Okay, that's how we generate the training data. I think this is probably quite unique compared to other groups. But the other question, how do I handle object without depth? Sometimes that object completely missing, does not even exist in the depth camera. So what we do is, again, we use our segmentation result. Remember each object, we take multiple pictures, and each picture we have the color-based segmentation. And if you get the color-based segmentation result, and you know the camera pose, you can compute the convex score. So you can compute the roughly 3D shape by intersecting those segmentation marks to get roughly the 3D shape of the object, and without the depth map. That's another strength of using multiple view. If you only have one view, you don't have a very good 3D shape. But if you have multiple view, even using the segmentation mask, you can get a fairly close 3D shape. And then we use that 3D shape as our post estimation to fit the 3D model. Okay, so here are some results. This is the segmentation result on the left hand side. This is the post estimation result. These are real data we record during our competition time, so it's not fake data. It's not just in the lab, it's actually during the competition. This is the post. You can see it works fairly well, sliding is off here. Like this one is actually very tough. There's only one part, slightly, there's a little bit depth here, there's no depth everywhere else, but we still manage to get the post. And this one is a little bit offset, but again, it's very difficult. There's almost no depth here. Here is another example. It's a very challenging example. The segmentation, you can see that sometimes after you get the post, if slightly adjust it, the segmentation actually if you can take the new segmentation inside the box, it actually works better. Okay, I'm going to show you some failure case. This one actually a failure case. The segmentation actually way off. This is our demo that run when we were there during demo day. So again, we have the cameras installed at the gripper. First of all, we take the picture of the shell so that we can calibrate the shell location. Then we start taking picture of the beam. You can see we take multiple pictures. So what we're doing now is looking from different view angle, trying to take many pictures. And after that, when we take each picture, we run the convolutional neural network, we run the background subtraction all together at the same time. And then now I think our program is a little bit slow, so that's why we're computing that, causing that. And now we decide to, do some action. And the MIT team, they are very smart. They design this gripper to smartly decide which way to put each object. I'll let Peter talk about that later in this workshop, how we do this part. But overall, what we're trying to do now is basically we're talking about we can use deep learning for 3D object recognition. But we focus in particularly for animal picking tracks is really instance level recognition task. Now we're trying to go beyond APC and going further. For example, let's go beyond instance level. Let's talk about category level. Like this is a really important problem in computer vision. Like even image, for example, 2D object detection, that's one of the most popular tasks in computer vision. Even 2D image, you want to output a 2D bounding box of the object, and then say that this is a trap. But unfortunately, it's not very useful for robotics again. For example, a robot needs to decide what to sit on the trap. Having a 2D bounding box is not very useful. At least you will need a 3D bounding box containing the object, including that pose or orientation in the space. This is different from APC because this trap could be a new trap you never see before, and no one tell you what trap you will encounter. So it's really a category level recognition problem. It's much more challenging, but at the same time, it's also very useful in certain tasks. So we model this task as the 3D model object detection. Again, we'll take a color image as input, depth map also as the input. And we want to output 3D bounding box for each object, recognizing the color of the box, encoding the object category. So if you look at 2D image, traditional 2D object detection, you have a 2D image as an input, you have the 2D box as the output. So you have 2D in, 2D out. Of course, you can imagine there are all 2D operations in between, basically doing 2D deep learning or either for segmentation or for detection. But another task is slightly different. We have a 3D input because you have a 3D depth map, basically it's representing the 3D world. We also want to have a 3D output. Of course, ideally, you can imagine we can get a 3D operation in between. But that's actually not what people are doing today. The state-of-the-art system is from Berkeley Group, from Distinguished School in Berkeley. What they do is they encode the depth map as one extra channel of the color image, and then they apply a lot of 2D deep learning operations and so on. Eventually, they do ICP fitting, just like similar what we do for the element picking challenge. But the problem of this approach is that while APC, you know the object for sure, we are talking about category object recognition. You don't really know the object shape, because even for the trap, there are many different types of trap in the world. So the ICP, which model you use to fit the ICP for ICP is actually unclear. So I would say that this approach is less ideal. It's just to approximation. Ideally, what would be a good approach is we want to have 3D input, 3D output, then you should have all the 3D operation in between. That's why we are promoting this 3D deep learning approach. Let's do deep learning, but everything in 3D. This is the algorithm I'm going to talk about. Our algorithm including two steps. One is the 3D region proposal generation. Given a 3D environment, you want to generate some boxes that may contain or may not contain the object. But if there's an object, there will be one of these boxes. The second step is for each box, you want to generate the category of the object. Let's talk about the region proposal first. Given a scene, you want to generate like thousands of candidate or boxes that may contain the object. So the first thing we do is we generate a major digression to estimate the major digression of the loop in order to define a coordinate system to represent this loop as a volumetric representation. And then we take this volumetric 3D representation to feed into a 3D convolutional neural network in order to generate a 3D object proposals that may contain those objects. Let's talk about how we represent the scene in 3D first. For image, we know that for any image, you can encode them as a 2D array that with the numbers encoding the intensity value of each pixels. But for 3D, it's similar. Let's say that you have a surface in the space, and let's cut them to have one simple slice. So it's just like the boundary like this for visualization. We can also define a 3D array. In one slice, then it's a 2D array. Basically, this is a function with the value defined on each location of the function. So we discretize it. The number here actually encoding the distance. If this is the number encoding the distance from discrete to the closest location in the surface. With further away means the distance is further away, so it's really a distance function. We also put negative, put a sign on the other side. If on the other side of the surface this is negative, this one is positive. So it's a size distance function. So I put all the numbers encoding the distance. For those numbers that are very big, it sometimes have a numerical problem, so we truncate them. So we have the truncated size distance function as the representation of the space. Okay, and then finally, now we already talked about how we represent the 3D volumetric representation. Let's talk about the 3D cone. As we all know that Yang LeCun, the godfather of deep learning, his biggest contribution is introduce convolution to 2D image. So for example, the idea is very simple. Let's say that you have a character. While you have these two blue boxes, while they are at different locations, they have actually very similar shape, just like this. Because they have similar shape, you can reduce the same filter for different locations, so you can run convolution filter all over the space. But what we're trying to argue is that this is exactly the same for 3D shape as well. Let's say that this is a 3D object. These two blue boxes, they are at different locations of the object, but they share similar local shape. So therefore, we can naturally extend convolutional neural network in 3D to do object recognition as well. So now we already talked about the representing the space in 3D. It's a good idea to do 3D convolution in 3D. The next step is how we actually design the network. What we do is we take a 3D scene as input, and then we feed into a network that can output some boxes for example, for small object. Because the receptive field of the object is actually very different. For example, for a small object, we design this network that can generate the boxes to contain smaller objects. But for bigger objects, how do we take care of that? Because some objects are very small, some objects are very big, then you cannot really use the same filter size to represent all of them. So what we do is we have another branch of the same network, but generating boxes for bigger receptive field, bigger area of the space. For example, like sofa, like that, like chair, like table, those bigger objects, it will be generated from this branch. So this is our neural network, and this neural network have two outputs. There's two outputs. The first output is the object is score. Basically saying, is there object in this box or not? Answering this very simple question, object or not, object or not. That's the question it's trying to answer. The other question it's trying to answer is the 3D box offset. There's a big 4 box location, but how do you adjust the big 4 box into a better way to fit the object better? So it's a regression problem that output a few numbers to adjust the box to contain the object better. So this is basically the first step, the 3D region proposal. The second step is about the 3D recognition. Given a box with containing an object, or may not be an object, you try to output the object category. So again, what we do is we represent it as a volumetric 3D representation. We feed them into a neural network. The neural network can output the object category. This time it's not just object versus non-object, but actually the object category, as well as again give the neural network another chance to adjust box again to fit the object better. So to implement this idea as well as to implement the convolutional neural network, what we do is the software-wise, we write our own software framework called Marvin.is. It's an open source deep learning framework. It's actually very useful for for robotic application, because we purposely designed this to actually compatible with the ROS. It's very easy to compile together with ROS and then just run it. We also support that hub data type that can save 50% of the memory, so that you don't need to have that much GPU memory to run the same network. It's very useful for 3D network because 3D convolutional neural network have way more parameters than 2D one, so memory suddenly becomes a problem. So it's open source, feel free to use it. It's actually used by real product in Siemens. So for some medical imaging, they also have 3D CT scanner and so on. So here are some results. You can see that the results are actually quite robust. For example, this toilet is heavily occluded, but you can recognize the full extent of the object. We're not just recognizing the visible part, but actually the whole object with that pose. But you can, some people may argue if you have the depth map, it's actually very easy, but actually not. Even with depth map, there's lots of things missing. The depth map actually not that reliable. Of course, the result also not perfect. For example, there are 6 PO here, but we can only recognize 3 of them here. We compare our results together with the traditional approach. Like this is our approach that we propose, is based on 3D deep learning. But you can also do 2D deep learning. You do deep learning in 2D and do ICP. This is what it does here. And we also can do 3D, but not deep learning, like training a support vector machine to do that task. But based on the comparison, you can see that this 3D deep learning approach is significantly outperform the 2D deep learning one, as well as the 3D non-deep learning one. So combining deep learning applying 3D maybe is really a good way to go for this category object recognition. Okay, so far I've been talking about instant level recognition and going beyond instant, how do I talk about category level recognition? And since I'm running out of time, I'm just going to touch a little bit at how do I go even beyond recognition. Right now we're basically saying that, okay, given object, you recognize what it is, that's it. But human vision perception system can actually do a lot of other amazing tasks. For example, given an image like this, without showing you the other side, you can kind of imagine or hallucinate what's going on the other side, right? Right, that's what you imagine. So ideally, you want to have this kind of capability. If I show you a map like this from the side view, you will have no idea this map from top view actually look like this. Because again, you have some kind of straight prior for you to hallucinate what it is. And it's actually very useful for robotic as well, right? You can decide where to go and so on. So we designed this 3D neural network to not just doing recognition, but actually hallucinate the shape. We train this neural network here is just some visualization of the neural network. For lower layer, it's just like corners, edges in 3D shape, and then it becomes object part. Eventually, it becomes the whole object. Due to time constraint, I'm not going to dive into detail, but just show you some visualization of what we learned with this kind of network. I'm going to skip this a little bit. Yeah, but with this kind of network, you can do for example, you can do sampling. You can ask the network to generate like 7 toilets for use, and then different toilets have different shape. To demonstrate a new network is not just remembering what is the shape of the object, but I can actually generalize it. You can actually use this for shape completion. That, for example, let's say that this is a side view of the sofa. You can actually hallucinate different shape of the sofa. This is a side view, a depth map. Depth map means you can only see one side of the object, but you can hallucinate the whole object. For example, you don't see the toilet cover, so sometimes it has open, it's closed, and it's all possible. What we do is we actually can use this for many other robotic tasks. For example, view planning. Let's say that you have an object, you take a picture, and you try to recognize the object, but you realize it's very confusing, and you have no idea what the object is just from single view. Naturally, you will ask the robot to move and see from another view, right? That's naturally the choice. But which view to choose is actually a problem that we need to decide. So it's the next best view problem that we're talking about here is like the active object recognition, which view to choose in order to minimize the uncertainty. But after you take that picture, you also need to integrate the information from multiple views in order to recognize the object. So this is also the integration problem. What we're trying to say is this 3D deep learning network can actually take care of all these tasks. The first frame recognition, the view planning, as well as the integration. Due to time constraint, I'm not going to talk too much detail, but if you please let me know if you want to know more of that. So I'm going to skip this a little bit. Okay, we do have some evaluation to demonstrate this is working. Okay, just in summary, today I'm talking about how we use deep learning for 3D object recognition. I start by talking about how we do that for instance level recognition in ML picking chain. And going beyond instance level, we evolve into category level, but we can also extend the deep learning algorithm from 2D segmentation to actually 3D object recognition. And finally, I also demonstrate a simple result for going beyond recognition, not just recognizing what the object is, but actually can go beyond that and, for example, do street completion, to do view planning. But what I'm talking today is really just one corner of our whole mountain. I only focus on the object level, we can do 3D deep learning for objects. But beyond objects, we can actually do 3D deep learning for the scene, taking the whole scene as input, we can feed into the network, and the network in single shot can recognize all the objects. Or we can focus on the deep learning on the local key point, a small local key point, and design a descriptor to characterize those key points for CM application or all kind of applications. Please check my website if you want to know more about that technical report published there. Finally, I also have one slide advertisement of a company. We just started a company in Silicon Valley working on autonomous driving. We're recruiting, so if you are a student or you are a professor, feel free to send me an email if you are interested in joining us. Okay, thank you very much. Question?
You showed some good results. How much labeling is involved, and how do you get all the labels? Usually, on the label is all basically, deep learning input labels.
Yeah.
And you got all kinds of scenes. Most people consider a few benchmarks for those scenarios. And if I get total different kind of clutter, what will happen in that case?
Yeah. For the ML picking challenge, we design a very smart way to use background subtraction to get the label for free. But for the second project I described, the category level object detection, what we do is we control our data set. We hire people. I spent probably $20,000 to hire people on the internet to draw bounding box for objects. Yeah, so we control our data set. Yeah, just manually, brute force. So we take a lot of pictures by ourselves, and I carry a depth sensor everywhere, take pictures, and then we collect the data, and then we manually hire people to manually label the 3D bounding box to do the training. It's not as big as ImageNet, but it's also very big in the sense of the negative data. We're doing object detection. We're not just doing object classification. So we're doing object detection. We basically doing sliding window everywhere, and at different locations, they will use it as a negative example. So we do get a lot of negative examples. Although we may get only a few thousand positive examples, but we'll have a lot of negative examples by just randomly cropping the space. It's actually good enough to train a network. A lot of people feel that if you don't have a lot of data, you may not be able to train a network at all, but that's not true. You can still train a network, just if you have more data, the network just goes better. In other there's also other ideas. Like for example, for this one, to train this network is a very big network, very difficult to train because it's talking about many objects at the same time. So what we do is we use computer graphics to generate certain synthetic data as well, and to pre-train the network. After we pre-train the network, we refine the network to the real data. In this way, we bypass the data problem. So that I think there are many hacks we can do to generate the data. You just need to be very creative. Thanks. Any other questions? Yeah.
The team that won the first challenge had a paper at RSS, which I think also won the Best Systems award, where they described their system, their approach, and they kind of were arguing for simplicity. And if I can channel them, I think the argument was as well, you should avoid trying to do 3D pose estimation. And perhaps detection is sufficient. But at the same time, do you think that given the progress in convolution neural networks and so on, perhaps it is a sufficiently simple problem that we should be solving? Or should we be trying to avoid it whenever we can?
Yeah, that's a very good but difficult question. I think the reason we have to get a 3D pose is Peter forced me to. If your gripper do not, or if you're just using the suction cup, you do not need the pose. I think the problem is indeed easier. The segmentation is indeed easier. But I do believe that if you really want to have a robot, not just doing Amazon picking trends, but a genetic robot doing all the tasks, you do need to get a 3D pose. That's my personal belief. Otherwise, a lot of smart reasoning, not just the grasping, but other reasoning cannot work. That is the chair up and down, upside down or not. If upside down, sure, you feel that this is a strange space, you want to small it. So I would say, yeah, in terms of application, we do certainly need to have the 3D pose. This 3D pose estimation is still a difficult problem, even if it's 3D. The reason, like for example, in this APC trend, you can see that we use ICP to get the pose, not instead of 3D deep learning network to get the pose. Is we actually spend like 2 months. Personally, me and my student Andy work together at 14 hours per day to get a 3D deep learning network to get the pose, but we cannot never really get the result. So that's why we fall back to the ICP-based approach. So it's not an easy problem to deal with. Yeah, but I still believe it's possible. Just we did not get something right, something wrong, and we didn't figure out what is wrong.
Do you have a theory on the? I'm very interested in your attempt into determining the pose estimation in this situation, but failed. Like, do you have a theory about why? What the major reason?
Yeah, one thing is we don't have training data, so at that time we use computer graphic to generate the training data. We have the 3D object scan, and we render it from many rotating the object render from many different views. And I think maybe this because the data is slightly different from the real data. That's one problem. The other problem is maybe there's too many degrees of freedom. Like right now, when we talk about object like chair, it usually sit up this way, and you know the gravity, right? But for Amazon picking chairs, you can put the object anyway, randomly. So there are too many degrees of freedom, and maybe we did not parameterize the rotation correctly. That's another way to parameterize it better. We try it for 10 years. We try almost anything, discretize the space and so on, anything that you could imagine, but you just never get it right. The network never really get trained to have a very good network. So I think there's a lot of more research to be done. Ideally, how we combine color with the depth together, that's another issue. The segmentation is actually very good because the color is easy to recognize object. While if you just purely based on depth, maybe it's very difficult. Also maybe because our depth camera is very bad, maybe if we use a better depth camera, that could also fix the problem. So I have a series of 10 things that could potentially go wrong, but I don't know which one is wrong. That's why we never figure it out. But maybe next year we can figure it out. Thanks.
All right, I think due to time constraint, we have to stop here, and you can feel free to ask Jianxiong for any question offline.
Thanks.
Now it's 10:20, so we will come back at 10:40 for the next talk. Yeah. Oh yeah. I have the video from the Delft team and the ACRV team. I will play it here, like during the coffee break.
We can have them in the beginning of the session. The beginning of the session. So that people will be displayed.
I think I'll play it.
Repeat it.
Yeah.
Hello again. Let's do that.